we shall try this. So here I want to implement my state diagram using window on the input. And so what I'm going to need to do here is basically detect the sequence 0, 1, 1. And so I need to keep track of 2 bits. D, D, Q, Q bar, Q, Q bar, clock, clock. And basically I'm going to need to detect when this is 0, this is 1, and the input is 1. So this goes in. So 0, 1, 1, and this all together. And if you're paying attention at home, this is actually more minimal than our minimal design. And this is one of the very fascinating and very interesting things about window on the input, is sometimes it is actually the simplest design possible. And so keep an eye out for that. And so we actually won here. This is actually our minimal. So this is actually technically should be the answer to both B and C. And the important thing is that basically it's using our states better, is really all it's doing. And so that's a lesson learned. And then finally we've got implement your state diagram using one hot design. And so since I have 3 states, I'm going to need 3 D flip-flops. So we need D, Q, Q bar. D, Q, Q bar. And D, Q, Q bar. And I'm going to do this the way I prefer to do it, which is actually writing out the expressions rather than using the decoders. You can use the decoders and you can use muxes as well. Both are actually extremely valuable, and I may actually change my mind once I actually start on this. But so I'm going to make this state A, this state B, this state C. So I'm going to have A, B, C. So I get into state A by having, this is QA. So QA ANDed with X bar, and having QC with, so this is QC. Oh, sorry, this is not with X, this is just with X, and then QC ANDed with X, and then that's just ORed together. And then here I've got QB, has 3 inputs, so this is going to have an AND gate, and it's going to be QA X bar and QB X bar and QC along with X bar as well. So pretty much this is just could be X bar again if you're paying attention. And then this one will be 1 when we're at QB. QB ANDed with X, and that goes into here. And E. E is a trick question, I'm sorry. I have to do that every so often as my requirement as being a teacher. But it's asking if the different implementations are equivalent. And, oh, sorry, I actually didn't finish this problem yet. I need to have QC ANDed with X for Z. But anyways, coming back to the question of whether or not these are equivalent. The answer is both yes and no. They are equivalent, yes, because the output is the same for every input sequence. In other words, they implement the same state diagram. That is one potential answer, and this is probably the one that I got the most. And the important thing is that they implement the same state diagram. You need to have either stated that, or that they output the same for every input sequence. That is how you can justify saying yes. You can also justify saying no, which I highly doubt anyone did, judging by the fact that you didn't guess that, is the fact that they actually use different states. The one-hot design has 1, 2, 3 flip-flops, so 2 to the third states, which is 8 states. It's actually a completely different state diagram. What's just interesting, though, is that it's going to have 5 of those 8 states will be unused, and so therefore they're radically different. And same thing with the window and the input. This is just inputting a shift register, and so its states are encoded again differently than the way I encoded them in the original problem statement. And so if I encoded the states better, I could have actually come up with the window and the input design with the correct encoding. But the state definitions are different than in the actual state machine, and so the encodings are different, so therefore in one sense they are not equivalent, and so those are potentially 2 valid answers.